Good evening, everyone. Okay, so this is likely to be the last lecture for this chapter. So we were solving this question. Wait a minute. Just a minute. I will start very shortly, right? Just in a moment. Uh, yes, Suchi, what happened? Can everyone please turn off their microphones? Okay, no problem. All right, thank you so much. Fine. Now I think we can get started. I hope everyone can see the screen. We're solving this question about a null point the last time, right? And we finished its part A. Right now it's time for the part B, right? Which is actually much easier compared to the part A, right? It's very straightforward. So what I'm going to do is we'll just you know, read this question from here. You all read it from your book. Verify this result for simple configuration, means simple system, right? Okay, of two charges of same magnitude and sign placed a certain distance apart. So I'm going to draw a diagram for the part B on the next page for over here, right? So it says that there are two charges of the same sign and same magnitude kept some distance apart, let's say some distance L. Okay, then we have to verify that if there is a null point, we have to verify that if there is a null point, that null point must be having unstable equilibrium, right? That's what we have to prove, or that's what we have to verify. So let's see, first of all, where is the null point. I'm sure you realize that if this is some charge q and this is charge q, exactly between the two, here the electric field is 0. So this point is the null point. All right. So over here we have got a null point. Now we have to show that this null point is unstable equilibrium. So let's say that there is a positive charge that you put over here. Suppose capital Q. Right? Suppose we put a capital Q charge over here. So this is in equilibrium. But if I will shift it slightly upwards, let's say we shift capital Q over here, then the force due to this Q charge will be in this direction, and the force due to this Q charge will be in this direction. Right? So resultant force by parallelogram method is in this direction, right? So this is the net force acting on it. You can see we shifted it upwards, right? This is null point, here is one charge, here is another charge, right? And we shifted it upwards, this Q. Then it does not come back. The force on it is not towards equilibrium, but rather opposite or away from equilibrium, right? So that means this is definitely unstable equilibrium, right? Because if you leave it over here, then because of the force it will just run away, it will not come back to the point N, right? Okay, so just like this, if you put a negative charge at the center, at the null point, suppose this is, these are the two charges. Now if we put a negative charge over here, right, let's say at the null point we put minus q charge, right? So then the unstable equilibrium idea will come up when you move this either left or right. Suppose you move this a little bit left side. So then the attractive force from this nearby charge will be more compared to the attractive force by this far away charge, right? So if I say, if I call these F1 and F2, this is charge 1, charge 2, right? Then obviously if you move it towards, if you move this minus q charge towards left side, then F1 will become greater than F2. So net force will be towards the left side, again left side, that is away from the null point or away from equilibrium point. So if you move this little bit towards left side, it will start moving towards there and hit that charge. So it will not go back to equilibrium, right? It will not go back to the null point. That means once again this equilibrium is unstable. So like this, in every case you can verify that, if you can actually verify in every case that if there is a null point, that null point will always be unstable equilibrium. All right. So with that, this B part is over. We verified it. All right. Okay. Now what we'll do is, we will not start the chapter 2. We will solve your doubts from the first chapter. Okay, we already have a question. So in first case, if we move null point, you can't move null point. Sorry, your question is not clear. You will have to think about what you are saying. You can't move a null point. Null point is just a point. You can move a charge, right? If you move this towards the left side, then the charge will come back. But that is not the point, right? Unstable equilibrium means even if in any one direction, unstable equilibrium means even if in any one direction, even if in any one direction the object runs away, right, then that is unstable. Okay, then that is unstable equilibrium. All right. So that's why it's not going to be stable. Is it necessary that in between two like charges there is a null point? Of course, Kia, it is necessary. Of course. Because if you have got two charges, let's say A and B, both are equal in magnitude, all right, and both are plus Q, right? So then the electric field at this point, C, suppose you call it C, right? You don't want to call it N. Then the electric field due to this left charge is KQ by R square towards right side, and due to this charge is KQ by R square towards left side. So these two electric field will cancel each other, right? The fields will cancel, and the net electric field or total electric field will be 0. All right. Okay, so that is how it's going to work, right? So between two charges which are like and have same magnitude, there's always going to be a null point. Okay, any other questions? What will happen is, what will happen if test charge is displaced slightly towards null point? Ramya, the test charge is already at the null point. From null point, you cannot displace it towards the null point, right? You must displace it either left, right, up, down, somewhere, right? Can it be stable equilibrium in any possibility? No. That's what this whole question was about. That even if you don't know anything about the electrostatic field, right, even then you can say that this equilibrium will be unstable, right? You don't need to know anything. We have proven that in any case the equilibrium is unstable equilibrium only, right? Stable is not possible. Ramya, did you understand the answer? Okay. Anything else? Are not no, are null point always need to be in? For electrostatic field it is true, right? For electrostatic field, that is the electric fields that we are studying here in this chapter, it is necessary that the null point will be, so null, at the null point there will be unstable equilibrium, right? That's what that's what I'm saying, and that's what we have proven in this A part, right? Always, yes, null points are going to be unstable equilibrium for electric field. Okay, anything else? uh, should we instead get started with chapter 2? Or will null point be always at equal distance from charges? If the charges are equal in magnitude, it will be. Uh, I think there is a question like this in the book. No. If the charges are equal in magnitude, null point is at the center. Otherwise, it is not. Right? Okay. Some of you are saying we should get started. Nobody has said no. How can we send pics of questions that we have doubts if we can't type them? Uh, well, Purvendra, I don't know what you are using. If you are using a phone, well, I have no idea because I have never used Zoom on a phone. Okay, but here in chat, uh, I think there is somewhere an option to send a file. Yes, when I click new share or share, it allows me to share a file. I don't think I've turned it on for you all. Let me check. Allow participants to. Okay. Yes, but I have not allowed, obviously. So you want to share something right now, Purvendra? Uh, I still can't turn it on. I will find it out and we'll do something like that the next time. Okay, right? Even I am not so good at all this, right? Okay, we have the next question from Jainam. In Gauss law, area vector for closed angle is acute if electric field is outward. Please explain. Okay. Right, fine, understood. I understood your question, Jainam. Okay. So the question is that if there is some closed surface, suppose this is like a, you know, let's say some, uh, just a minute. This is some closed surface of random shape. All right. Okay, and at some particular point here, because this is a curved surface, you cannot draw one area vector. You'll have to draw multiple area vectors by dividing this into small parts. So if we do that, here we get a small area vector for this small area only, right? And now suppose the electric field is outwards. Let's say something like this, all right, in some way. So you see that E vector going like this, E vector is like this, and the area vector is also somewhere in this direction, so this angle is acute, right? But on the other hand, suppose the electric field is inwards, then it would look like this, that the electric field is coming inwards and the area vector is going somewhere outwards, right? Because area vector always area vector is always outwards, right? Remember that area vector for closed surface is always outwards, right? So if area vector is outwards, then based on that this angle will be obtuse. Jainam, I hope you understood what I said. It is due to geometry, right? It is the way geometry works, right? Okay, we have the next question already. The question is, why electric field is normal to the surface in space at each point? No, Shivangi, the question is wrong. Do you mean normal to conductor? Do you mean normal to sphere? What is your question exactly? Normal to what? Normal means perpendicular. Perpendicular to what? Others, if you have questions, please start asking those. Hurry up, come on. I'll take your questions one by one. Okay. The normal to conductor part, I think I'll leave it for the second chapter, right? In second chapter, there is a detailed theory about this idea, right? Okay. It is possible it's given somewhere in the first chapter, but trust me, it's easier to understand in the second chapter. Okay. Force between 2 point charge is if dielectric constant. Okay. Dhruti, we are going to solve questions related to dielectric constant later, right? Because dielectric constant is in full detail in second chapter. All right. So again, any question with dielectric medium or dielectric constant, that we can leave for second chapter, right? This is for everyone. If you see such questions, what is the flux through cube if charge q is placed between the line joining the corner? Okay. Well, I need to have a clarification. Suppose this is the cube. Dhawal is saying that if we put a charge q at the line, on the line joining the corner. So Dhawal, do you mean corner 1 with corner 2, or do you mean between 1 and 3, or do you mean between 1 and 5? Because answer will change depending on that. 2 and 3. Okay. Interesting. 2 and 3 is same as 1 and 2. So edge, right? That is called edge, correct? Right? This is an edge of the cube. So if you put it on edge of the cube, what will happen? Let's discuss this. If you remember, okay, if you remember that when we consider this point charge q, right, to create symmetry around the charge, listen to this carefully, to create symmetry around the charge from one cube, right, and the charge is over here, I'll have to create one more cube like this, and one more cube like this, and one more cube in this way. Similarly, I'll have to create one more cube here, one more cube here, like that. I hope you're getting it. Okay. So I'll have to create symmetry around this charge, right? So for that we have to construct surfaces or construct objects. So because this is at the edge, you can also imagine it in this way. If you take a corner of your room, see this edge, vertical edge or horizontal edge, everything is same, right? If you make a hole here, right, in how many rooms will that hole be made? You think about it. I'll repeat. If this is a corner of your room, if this is your room, okay, a cubicle room, and let's assume that there are such cubicle rooms everywhere. So if you make a hole at this place, in how many rooms will there be a hole? I'm asking the question to everyone. Listen to this. The question is, if you take a room and at the intersection of two walls like this over here, if you make a hole, in how many rooms will there be a hole? Okay, I've started to get some answers. Very good. Continue, people. Continue. Most answers are right. Very good. Okay, well done. Right. Correct answer is 4 rooms. Right. Okay. 4. See, you'd get a hole obviously in this room. You'd also get a hole in this room here, right, which is next to this wall, and then you'll get a hole in the room that is behind this room, all right, and then you'll also get a hole in this corner one, right? Okay, so like this you'll get hole total in 4 rooms. If we would be in the class, perhaps we might take a drill and make a hole and then we'll prove it, and you would have enjoyed it a lot. Okay, but obviously we are not going to do it here, right? So this is how you get it in 4 rooms. Now, what does that have to do with this question? It is that if you place a point charge in that hole, then the field lines coming out from that hole, field lines coming out from that charge or from that hole will be equally distributed or symmetrically distributed in these 4 rooms, correct? Or 4 cubes. So for one cube, it is going to be total flux divided by 4, right? So in 1 cube, it will be total flux divided by 4. So total flux divided by 4 means Q by 4 epsilon 0. All right. Well, I hope you understood. And everyone else also, I hope you understood this, that total flux coming out from a charge will be Q by epsilon 0. And now this is 1/4 for one room. Okay. Now we are going to next question. The next question was by Vivek. Okay, Vivek was asking, can't understand where to use Gauss law and where to use Coulomb's law. Okay, I'll just say it very shortly. Vivek, we should use Coulomb's law generally for separate or point charges, right? That is, if you want to find electric field, of point charges, you generally use Coulomb's law. And if there is a lot of symmetry and there is continuous charge distribution, right? If there is a lot of symmetry, okay, some kind of symmetry, either spherical or like a flat surface or like a wire, okay, if there's some kind of symmetry and there's continuous charge distribution and you want to find electric field, then you use the Gauss law. Remember, both laws are always valid, but sometimes this is easier, sometimes the other one is easier. Okay, right, fine. Let's take the next question. The next question is, electric dipole is placed at center of sphere. It's by Purvendra. Okay, then flux at the flux of electric field through sphere is 0. Okay. Hmm. Right. Fine. So Purvendra is asking a simple yet interesting question. Okay, your questions are in waiting list. Everyone, please wait a while. So the question is that suppose this is some sphere, right? And at the center of that sphere we put a dipole. Okay, so this is the dipole, right? Okay, so now based on that we have to check the options. Flux of electric field through sphere is zero. Yes, option A is right. Okay, like this, then electric field is zero at every point on sphere. No, obviously, because this, oh sorry, yeah, obviously it's not zero everywhere, Purvendra, because at this point and on this point, this is on axis, right? Electric field on axis is not zero. In fact, we have derived a special formula for that, haven't we? And similarly over here also on the bisector also it is not zero. In fact, it's not going to be zero at any point, right? So like this you will be able to evaluate all the options. Okay, I hope Purvendra I have answered your question. Now we go to the next question, and that is by Rutva. If charge was at circumference of sphere, then flux through the sphere is. Okay. Okay, I'll just indicate what this question is. You will not be able to solve this because of the requirement to do calculations related to solid angle, right, and flux. Okay, so we will just talk about this theoretically. All right, it is that if you take a sphere, right, like this, and let's assume that the point charge is exactly on the circumference, right, over here. So what happens is that the field lines coming out from this point charge, they're, they're going in all directions. All right, okay, but you realize that half of the field lines go on the left side, right? Okay, and half go on the right side. So you could say that for such a situation, half of the flux is passing through the sphere and half of the flux is not passing through the sphere. So that's why the flux is only half of what a charge has, right? So total flux for a charge is q by epsilon 0, but for this sphere, the flux passing through that sphere will be only half, that is q by 2 epsilon 0, because over here the field lines, half of them go towards left side, that is go into the sphere, and then half of the field lines just go out, right? So you can say that half of the charge is inside the sphere. So Rutva, the answer to your question should be q by 2 epsilon 0, but you cannot, this is not at all easy to do integration and derive, right? It's not impossible really, but I think you need to do a lot of calculation, right? You'll have to convert this whole sphere into rings or discs. Actually either would work, and then do some integration based on that, and we can get the answer like that. It's very long. Some field lines also go up, agreed, but practically the number of field lines is arbitrary, right? Okay, so it's not that the field line going up and down are only two compared to everything else, right? There's only one field line that can go up and only one field line that can go down. All the other field lines must go at an angle, and if they'll go at an angle, then they will definitely go through the surface of sphere, right? Because that is what it is like, right? Only one field line will move up and only one field line will move down, right? Except that all the field lines are going through the sphere. Okay, Raj, your question is in waiting. There are many more questions that I have to answer. The next question is by Hodel. If we take such diagram of cube, then in which direction will area vector be? Okay. Sorry, Hodel, your question was related to Dhaval's question, but we are only coming to it right now. So you are asking that if we take a cube then what is the direction of area vector? See, for flat surface, area vector is very easy to decide. Okay, but this is some collection of flat surfaces. So what we do is we divide it into 6 parts. All right, with 6 parts, 1, 2, 3, like that. So every surface has its own area vector. This is area vector of first surface, this area vector of second, this area vector of third, and so on. But remember, for a closed surface, area vector must always come outwards and perpendicular, right, from where it is coming out. Okay, I hope, Podil, that answers your question. Can we decide of diagram? I don't understand what you're asking, Podil. Can we decide of the diagram of 4 cubes? No, I didn't get what you are saying. You can try typing it again. I'll take your question, right? Meanwhile, I'll go to the next. Okay, next question is by Dhruti. Why should electrostatic field be 0 inside a conductor? Dhruti, I will answer this in second chapter. In fact, there's a theory in the second chapter that talks about this same question. All right. So this question will be answered in chapter 2. I'll answer your other question. Which orientation of an electric dipole is in uniform electric field would correspond to stable equilibrium? Well, see, if electric field lines are like this, stable equilibrium will be when torque is 0, right? And the situation is favorable. So torque is 0 in two situations. One like this and the other like this, right? So this is situation 1 and this is 2, right? Okay, so in situation 1, dipole moment is towards the in opposite direction of electric field, right? That is situation 1. Okay, in situation 2, the dipole moment and the electric field are in same direction. So actually this situation is stable equilibrium, and so this is stable equilibrium for dipole and this is unstable equilibrium for dipole, because obviously positive charge likes to go towards the electric field. That is, if you disturb it, if you turn it, it will go back, but if you turn this one, it will not go back. All right. Okay, then why two field lines never cross each other? Okay, Raj, I think we have answered this in theory. I'll just do it very fast. Suppose two field lines cross each other like this. Then at this point of intersection, you can draw two tangents, one like this, one like this, right? But tangent direction indicates direction of electric field. So at one point, electric field cannot be in two different directions, right? This is impossible, right? At one point P, electric field cannot be in two different directions. So that's why they will never intersect. Okay. I'm so sorry, Koral. I still cannot understand. I understood you're talking about the hole that we thought of in the case of 4 cubes, right? But you cannot find the area vector over there, right? Because every surface will have a different direction of area vector, right? So there's no common direction, right? But like I explained, it will be outwards normal. Okay. Why do protons in nucleus of an atom do not fly apart? Avinash, this is just a basic question, right? It has something to do with strong nuclear force, right? This will come in chapter 14. All right. Next question. So stable and unstable equilibrium for a unit positive. What does that question mean, Chaitya? I don't know what I should explain. You're not even completing the sentence. Okay, Dhruti, why must electrostatic field be normal to surface at every point of a charged conductor? I said it earlier, again, chapter 2, right? Okay, now we are out of questions. I'm waiting for your questions. That's how I explained yesterday. Which number? Can you say the number, Chaitya? It will help me. Others, I'm waiting. If you have got questions. No more doubts. I believe you all have been given my phone number by the school, and I believe you have also been told about a time. No, that's strange. Okay. Don't you get messages from school uh, regularly which tell you about these meetings and everything on your WhatsApp? The number was sent to everyone on that by the school on WhatsApp. Lots of 11th standard students have sent me their queries like that sometimes. Okay, no problem. Right? I will ask Sunil sir to. Okay, fine. I will ask Sunil sir what's to be done about it. Right? I thought it would be given to you. Anyways, we have the next question. Let's go to the next question. The next question is: cone lies in uniform electric field. The flux entering the cone is. Okay, that's actually a very good question. Okay, so suppose this is some electric field which is uniform E, and inside it there is a cone. Okay, right? Inside it there is a cone. Okay, but see, this cone is a closed surface, right? And there is uniform electric field everywhere here. So whatever is the number of field lines. Sorry. Okay, so whatever is the number of field lines going in, right? Whatever is the number of field lines going in from this surface, that same number of field lines will go out from this surface. So whatever is the inward flux, that will be cancelled by the outward, right? Because we take outward positive and inward flux as negative. So total flux will become zero, right? Okay, yes, the total flux will become zero because this is a closed surface, right? There's another way to say it. Because the field is uniform everywhere, it means inside this there is no charge, right? So this is the second method. If there is no charge inside it, it would mean by Gauss law, flux is equal to charge enclosed divided by epsilon zero, but charge enclosed is zero because there is no charge inside it, right? So that's why the flux is also zero, right? I hope Prati you have understood. Okay, let's go to the next question. Uh, the next question was by, okay, I lost it. So sorry. Yeah. Jai, this is your question. An electron of mass m and charge minus e enters perpendicular to uniform electric field. Find the vertical deflection of electron and the angle at which it will emerge out of field. Jai, I think for this question, it would be good if you remember or try to recall what was that plates question. You remember that a particle of mass m just goes off like this. We found the vertical deflection, right? For that you need this distance x or L. That was L given in that question, right? Okay. So like this is what you have to do, right? So vertical deflection can be found easily, right? This is same as book question. Okay, same as textbook question. All right. Okay, but what about angle? See, if it comes out at an angle like this, right, you can actually take velocities components. This is Vx and Vy, right? So if you find Vx and Vy, then based on that you can do tan theta is equal to Vy upon Vx, and that will give you the angle, right? Okay. Right, did you get it? Okay. Let's go to the next one. Next question, next question. Who asked the next question? Okay. Fine, guys, question done, and now we go to, okay. Net charge, net charge, Srishti, this is your question. The net charge in the region where electric field is uniform at all points is always zero. Net charge in the region where electric field is uniform at all points is zero. Uh, yes, except where the field lines start and where the field lines end. That is, suppose you consider that there are two sheets, okay, like this large sheet, and I hope everyone remembers that the electric field due to large sheet is sigma by 2 epsilon 0 because of one sheet. But if there are two sheets like this, then the total electric field between the two sheets is sigma by 2 epsilon 0 plus sigma by 2 epsilon 0, which is sigma by epsilon 0. We did this in a question, right? Okay, so it would be that the electric field due to two such large sheets would be uniform because the magnitude doesn't change and the direction doesn't change, right? It will be uniform between these two sheets. So you can say that where the field lines start, that is here close to the sheet, right? Over here it starts, and then in this whole region, between the sheets, it is uniform. All right. So that actually because there is no charge, right? Because if there would be a charge, suppose it is like this, and you put a, let's say, a positive charge here, point charge. So what will happen is because of that positive charge, the electric field lines will go slightly away from that positive charge, right? Because of the effect of the positive charge, right? Okay. If similarly, if you would put a, a negative charge over here, then some of the electric field lines which were going straight earlier will now come in like this, right? So like because of such things, it is quite clear that if the field is uniform, then in that region there should be no charge, right? You can actually prove this with Gauss law also. It's that if this is some uniform field, you can draw arbitrary shape Gaussian surface, right? Again, I'll repeat, you can draw arbitrary means whatever you want, right? Any kind of Gaussian surface, right? Any shape. Always, for all such Gaussian surfaces, you get sigma q enclosed as 0. So if you take minute or infinitesimal Gaussian surface, then also you'll get sigma q equal to 0, right? So that would mean at every point the charge enclosed is 0, right? You can take such infinitesimal Gaussian surface, right? Srishti, have you understood that? Okay, we go to the next question. Right. Avinash, I'll do something about it. I don't know whether you sent it to the school, right? Because the school has not sent me anything, right? I will contact the school and find it out, right? Saitya is asking question 32. Yes, okay, right. I understood now what you are saying, right? We are talking about the null point, right? Okay. Stable and unstable equilibrium for unit positive charge. Saitya, do you want to know what is stable equilibrium? Is that what you are asking? Do you want to know the meaning of these two? Then what do you want to know? You don't want to know the meaning. What do you want to know? Okay. Uh, what is motion of positive charge? Well, see, that depends on the actual question, right? It is that because this point is going to be null point, and then this is going to be unstable equilibrium, right? Then it is possible that in one direction, right, in any one direction, maybe left, right, maybe up, down, maybe tilted like this, maybe in 3D, in any one direction at least, it will not come back, right? In any one direction, it will go away, right? If you disturb it, right? So that's why it is unstable. But you can't really say in how many directions, right? It really depends on situation. For example, when we solve part B, I hope you remember what I told you here in part B. In part B, if you take two positive charges and you put a positive test charge here and you push it up, then it will keep going up. It will not come back. But if you push it left or right, it will come back because there is repulsion on left or right. Okay. So it really depends on the situation, right? Of what kind of other charges are there, right? Like that, if you take two negative charges and you take a positive charge here, right? Then what's going to happen if you push it up, it will come back, right? Because these two negative charges attract. Okay. But if you push it sideways, suppose you push this a little bit towards the side, then it's going to be attracted, it will not come back, right? So that's what I'm saying, right? It depends on the situation. How it moves, it depends on the situation. All right. Next question is by Manav. Intensity of an electric field depends on distance r due to dipole L. Okay, okay, right. Manav, that's a very simple question. Let's see. I hope you remember that the electric field due to dipole, we derived a relation. It is minus 2k p vector r divided by r square plus a square. No, sorry, divided by r square minus a square whole square, right? This is on axis. And sorry, no minus sign. Yeah, on axis. Now on equator, we have it as minus kp vector upon r square plus a square raised to 3 by 2, right? This is on equator or bisector, right? So based on that, if you take small dipole or short dipole, that is a is very small compared to r, then you can say that in both cases, by simplifying, you will get E is equal to, in suppose axis case, you will get E is equal to 2 kp r upon r raised to 4, right? Because you are neglecting A. So now r raised to 4 is cancelled, so you get r cube, right? So in short, electric field of a dipole will depend on 1 by r cube, right? Okay. So the answer to that question is 1 by r cube. Next question is, what is meaning of alpha particle? Okay, Prachi, alpha particle means nucleus of helium, right? I think you would have learned it in chemistry perhaps. Alpha particle is nucleus of helium. It means it has 2 protons and 2 neutrons. All right. It's just informative thing, right? Okay. Does the force on charge due to another charge depend on charges present nearby? Okay, Darshi, interesting question, right? That is, do other charges affect the force by a charge? Well, the answer is no, right? That is the superposition principle, right? It is that if you take, let's say, two charges Q1 and Q2, then the force between them is obviously given by K, Q1, Q2 by R12 square, R12 hat, the Coulomb law. Even if there is a third charge, then that third charge does not affect the force between 1 and 2, right? So that is why we could find the total force on first charge by doing something like this, right? So we treat the pair independently. That is, force between 1 and 2 does not affect the force between 1 and 3, right? So presence of other charges does not affect. All right. That's why it's called superposition principle. Okay. Then, okay, then sir does depend on question for negative. In that particular question, it was given that we have to take positive, right? Okay. If you would have, basically it's all about two like charges. That's it. You could either take two positive or two negative, but unstable equilibrium will always be there. That won't change. All right. Now on to double question. When two pairs are having this, okay. Now they're coming back. Okay, I'm right. All right. Okay. All right. So well, I understood your question. We'll take it very quickly. Okay. It is that if you take two spheres with charges 2q and q, I think there is some example like this, and there's some exercise question also where you touch the sphere, right? You make the spheres touch each other, and so that's why charge gets distributed, right? I hope you all remember that idea. When two spheres touch, the charge gets distributed. So like that, if these are 2q and q, place some distance r, all right, and now you connect them by a conducting wire. Conducting wire is one that will pass charge, right? It will allow charge to flow. So because if these spheres are identical, right, identical, that is same, so that's why when you connect them there should be balance, right? There should be balance. So what's the total charge? 2q plus q, that is equal to 3q. That total charge will be identically distributed. That is, finally it would become 3q by 2, 3q by 2, half on each, right? Okay, it would be equally distributed because the two spheres are identical, right? So now if you want to find the force between these two, then that is going to be k 3q by 2, 3q by 2 divided by, okay, sorry, the charge was minus q, right? Fine, never mind. Okay, it's fine, right? So this is how you do it. Fine. So the whole question is done. Next is, okay, we still have 2 minutes. Why don't you type your question if you have any? How does Coulomb force between 2 points depend on? Ramya, like I said, dielectric constant of medium. We are going to talk about dielectric medium in the second chapter. All right. At that time, you will be able to understand this very easily. Okay. There is a separate topic of dielectric in second chapter. New chapter for tomorrow, of course. If you don't have questions. Okay. 5 balls are suspended with thread separately. Will we get these live lectures in school? Okay, I'll try if I can do it, right? I mean, it is possible if we can do some kind of recording. Although I'm not guaranteeing it, but I will try. Okay. So we'll take Arshad's question, which is actually very interesting one. So I'm going to copy that question here so that everyone can see. All right. Fine. I hope all of you can read this question now. Okay. So what we have got is 5 balls are suspended with a thread separately. So there are 5 different balls. Let's call them like 1, 2, 3, 4, 5. I think that's given in the question. Balls pair 1, 2, 2, 4, 4, 1 have attraction, right? So between some pairs there is attraction, and between some pairs there is repulsion, right? So between 1, 2, 2, 4, and 4, 1, there is attraction. Okay. And between 2, 3, and 4, 5, there is repulsion. So this is very interesting. See, do you remember? I think I did mention in one of the videos that repulsion is the true test of charge. right? Okay, because a neutral body is attracted by charged particles. Neutral body is attracted by charged particles, right? That is because of creating dipoles and non-uniform field and all that. Okay, that's why comb attracts the pieces of paper. So only repulsion gives true test of charge, right? So it means 2 and 3 are unlike. Okay, 2 and 3 are unlike, and 4 and 5 are also unlike. All right, 2 and 3 are unlike, and 4 and 5 are unlike. Now, okay, it is given that 2 and 4 attract. 2 and 4. Oh, sorry, I made a terrible mistake in a hurry. I'm so sorry. I was saying it wrong. 2 and 3 are having repulsion, so they are like. I'm so sorry again. 4 and 5 are also having repulsion, so they are like. Okay, so 2 and 3 are same, 4 and 5 are same, right? Okay, but now we are given that 2 and 4 are having attraction. That means one is positive and the other is negative, right? That means one is positive and the other is negative, right? Okay, so if you consider, look at 1 here. 1 is having attraction with 2 and 4 both. 1 is having attraction with 4, 1 is also having attraction with 2. But 2 and 4 are having attraction with each other. That means they are unlike. So if 4 is positive, 2 is negative, right? But this 1 is having attraction to both positive and negative. I'll repeat, 1 has attraction to both positive, 1 also has attraction to negative. That is only possible if 1 is neutral, right? Because neutral bodies are attracted by charged particles, right? Okay, so that means 1 has to be neutral, right? Arshal, I hope you have understood that. Okay, with that we end this class, right? So that you can continue with your next one. All right. Tomorrow we are going to start with the chapter 2. Goodbye.